Good day, folks. I just want to drop a few lines about science, the nature of science, the difference between the two arms of science, and that is pure science, or what we call basic science, and applied science, or what can also be called technology. All right, so this is a short 12 slides, and again, just to give you a big picture of the kinds of science that are out there and a little bit about what drives science. We'll learn more about the scientific method regardless in separate lecture. So on this first slide here, you can see basic research leads us to a greater understanding of how the natural world operates. All it's focused on is understanding how something works, or that something works in a certain way, or that it is made of this particle or that particle or molecule or electricity or whatever it is. As the microscope kind of entails, we're just kind of looking deeper into it. If you've ever caught yourself wondering, I wonder if, boom. Those are basic research questions, and they play a big role. The applied scientist takes that information that the basic research scientist has discovered, and they apply that to develop useful applications from the knowledge gained in that research. So, of course, rocket fuel, getting to space. What space is made of, what gas is made of, how to build an aerodynamic rocket. These are all applications of other kinds of knowledge. So the functions of science are twofold. We all know someone who is, a gadget maker or fixer, and perhaps you know someone with a love for exotic pets, like fish, reptiles, spiders, etc. I have a friend as a kid. I met him when he was about 10. I was an older teenager, so wasn't a friend I hung out with, but my younger sister did. Anyway, he collected snakes. He lived in a trailer park that had a pond, and there was always snakes in there in the evening, and he loved just getting the little john boat or canoe that he had, paddling out there. And in his bedroom, he had 10 kind of makeshift and a few terrarium where he kept wild snakes. Garter snakes, most of them. He got bit several times, none of them by poisonous ones, and he kind of got used to it. He'd just be like, ah! And he'd pop the snake off and keep it in his hand, and he'd put it in the bag. And you know what? He's a grown adult. That was years ago, and he still collects snakes. A lot of times he gets pulled over by the police thinking he's out in the woods doing something mischievous, and nope. And he shows them the snakes in the back, and then they run him off the property. Anyway, so, some people just have that natural curiosity about things, and they want to understand, or why they have an affinity for birds or cats or dogs. We're all born with these natural curiosities. The applied scientist wants to make some kind of practical use or new technology based on what we know. Both of them make the world go round. So pure science is the search for knowledge and facts. Applied science is using knowledge in a practical way. I would say probably the largest role of a scientist in what drives any, whether applied or basic research, is this cause and effect relationship. Where does sickness and disease come from? What's the human behavior behind smoking? Does one cause the other? We can very rarely answer these questions definitively. And so in science, we don't often use the word prove. You'll hear that word, and often even scientists will use the word prove, but they don't really mean I proved it. What they're really saying is that this idea is supported by this evidence. It may not be in all situations at all times. There's always context. There's always environment. There's many things that influence the way this world works. So cause and effect relationships, some are really easy. If I drop this ball and it hits the floor, the reason it bounced is because I dropped it. That's some pretty easy cause and effect, but those are the fundamental questions that scientists are seeking to answer. Pure science, the search for facts about the natural world. Pure science is often funded and conducted at universities, colleges. The basic understanding of why and how things work and react as they do are discovered here. The goal in pure science is not to make money. It's usually just to understand. The person is driven by wanting to know and just to do science. This is the geek, right? Industry typically funds the research at universities in hopes of just taking what is learned and they try to make a marketable product to make money. And that's how they fund more research and improvement. This kind of synergistic or mutual relationship between business, community, and academia is beneficial to both sides. Usually make a pretty decent wage just doing pure science. And then, of course, it helps the citizens, it helps society when people and business people take these things and make something marketable, make something useful, some technology. So in science, we often try to establish that cause and effect relationship, and it's driven by curiosity, the need to know, to explore, to conquer something new. It's that practical application of scientific discoveries, also known as technology. So just to give you an example of some things that come to bear out of the desire to progress, NASA's problem, they were trying to figure out how to get a helmet because temperatures vary so widely on the moon or say Mars. You might be below freezing at night and you're going to be 120 degrees at day or even 212 degrees. That's a pretty big shift, and the person inside this suit has to be able to survive in both temperatures. And they got to be able to see where they're going. So designing a face shield to protect and provide clear vision, something that can withstand differences. If you've ever, and I have, had glass cooking on a stove and then put it in the sink, crack, right, real cold. Or likewise, cold going to really hot. Corning glass failed at that. But in so doing, they succeeded at great cookware that can withstand extremes in temperature. So oftentimes in science, discoveries are made serendipitously or by accident. People set out with a goal in mind and then they discover something else quite remarkably. Sweet and low, the sugar substitute, that was an example as well. As many of you have heard that one, rat poisoning, but turned out to be sweet and it was a nice artificial sweetener. I know there are a lot of opinions there on aspartame and those such. Another example is saccharin. So you'll see table sugar or cane sugar. Oops, that says canned sugar. I should say cane sugar. Table sugar, sucrose, is made of two molecules, one glucose, one fructose. They have the same formula, just a slightly different arrangement, and you can see that here. So you dehydrate this, you take out the H2O, and you get, by putting it with sulfuric acid, and you get this new molecule, and it's called saccharin. This is a compound that is several hundred times sweeter than cane sugar, and it's used as a calorie-free sweetener. This is an application of knowledge that we've learned about sugar and the chemical formula. The risk-benefit analysis, and that is to weigh the pros and cons before deciding on a lot of these things, such as a sweet and low. As we're looking for rat poison, didn't work. Oh, but it tastes kind of sweet on my tongue. Hey, let's make a sweetener. Well, no, it didn't go quite that quick and that easy. Someone had a new idea that went many rounds before that was ever released to the public as something to be used. There's just so many considerations in each case, so 50-50 thinking rarely applies. Maybe if we do this, no, we don't want a maybe. It's got to be pretty well founded. So, how does scientific knowledge advance? Your natural curiosity. Sometimes we're too busy and too distracted in the world to let our curiosity go. That usually happens when you're a kid, right? But as you hit those older teen years and then become a young adult and life's responsibilities kick in, we kind of lose some of that curiosity. It's kind of a passing thought. But if you allow yourself to be curious and you make good observations about the world around you, you can often settle on some determinations just with a little bit of a few thought experiments. Fleming is a biologist, and he was known to be curious about everything. In particular, he was curious about a moldy orange in his lab once, and so he made a microscope. He made a slide and noticed that there was no bacteria on that mold. It was his curiosity that helped him to discover then what became penicillin. We'll see Charles Martin Hall. He's back in the day, in the 1800s, he determined to find a method to extract aluminum. So he did some aluminum mining. It used to be that it was $500 a pound because of the arduous process of pulling out aluminum out. Well, he developed a method to extract it, bauxite, and now 1 pound of aluminum, or at that time then, would only be about 30 cents to process. So, anyone that can come up with a cheap method of producing anything would become rich and famous. In this case, it was aluminum, and because of that, Hall became pretty much known as a father or started the foundation of the aluminum industry in the United States. So as you can see, the functions of science vary. It just depends on the kind of questions you ask and the kind of testing you do. Just trying to find out how something works for the sake of knowledge, or are you trying to make something useful that everyone can use in a practical way? This is the difference of pure science and applied science. That's why I enjoyed agricultural science, because I've used knowledge of plants and genetics to an applied aspect, which is improvement of, say, grapes, or the improvement of walnuts, or the improvement of, you name your fruit or crop, right? So it becomes a pure science that is applied, and we need both of those things to improve the world, to advance civilization. Okay, we'll see y'all in the next video.